In Chapter 4, we're going to begin looking at probability. Section 4.1 is going to be our basic concepts of probability. The learning objectives you will learn in this section is to identify the sample space of a probability experiment, use the fundamental counting principle, distinguish between empirical, classical, and subjective probability, determine the probability of an event's complement, and interpret probabilities. Probability and inference. Probability involves making judgments about how likely something is to occur. When we do inference, we need to determine if we see a study's results as possibly occurring by chance or not likely to occur by chance. For example, a company claims, "We have developed a sex selection process that greatly increases the chances that a baby will be born a girl." So if a company is claiming that they have developed a sex selection process that greatly increases the chances that a baby will be born a girl, we could test this claim by using their process on 100 births and count how many girls were born. So we have test A. Suppose we observe 55 girls or more being born. Okay, so that when we're talking about a probability, we're going to say that we observe 55 girls and 45 boys. Well, we know that the chances of a girl being born with no sex selection process should be about 50. So that's why we are doing this comparison here to 50. So 55 is greater than 50. But it's not unusual. That's not that big of a difference, right? We're looking at 55 to 50. There's only 5 more. So if we found that probability, and you're going to learn how to find these numbers later, it is about 18.4% to see this result by chance. So meaning no sex selection. So then this study would not strongly support the company's claim. Now let's take a look at test B. So test B says, suppose we observe 75 girls and 25 boys. Well, if we're doing that comparison again, 75 is greater than 50. This is a lot difference here, a bigger difference. So we would say that's very unusual. And if you found that probability, it is about 0.000003%. So this is a very, very, very small probability that 75 girls would be born out of 100. So this study would strongly support the company's claim. So the basics of probability. An event is any collection of results or outcomes of a procedure. A simple event is an outcome or an event that cannot be further broken down into simpler components. The sample space for a procedure consists of all possible simple events. So that means that the sample space consists of all the outcomes that cannot be broken down any further. So let's look here at some examples. Let's say the procedure is one person takes a drug test. So the event would just be pass. That is a simple event. The sample space, though, would be pass or fail. So you're giving both possibilities that could happen for one person taking the drug test. Now, what if 3 people take the drug test and exactly 2 pass? Okay, so this is not a simple event because it can happen multiple ways, and you can see that here. You could have a pass, pass, fail, a pass, fail, pass, or a fail, pass, pass. Now, each of those are simple events on their own, but if I'm looking at the events that could happen of exactly 2 passing, there are 3 different possibilities there. Now, if I'm looking at the sample space, remember, this has to be every possible outcome. So you see we have a pass, 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 a pass, pass, fail, a pass, fail, fail, a pass, fail, pass, fail, pass, pass, fail, pass, fail, 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 pass, and fail, fail, fail. Okay, so this is every event that could happen, or every simple event that could happen. Let's look at another example. We have a busy intersection. Let's say the procedure is to observe a busy intersection and count how many traffic accidents occur in a day. Your outcomes would then be a number. whatever number of accidents would be your outcome. So 2 or 3 or none. So these simple events are all numbers, and it's the count of accidents. The sample space would be the list of all possible simple events. So 0, 1, 2, 3, 4, and so on. A non-simple event would be a description of a set of outcomes, like at least one accident, because then you're saying 1, 2, 3, 4, and so on. So let's look at another example of eye color. Let's say that the experiment is to observe each person who enters the room and record their eye color. A simple event could be blue, or it could be brown, or hazel. Okay, so notice that I'm using eye color. The actual eye color that is observed would be the outcome. Okay, or green. All the different colors that you could say eyes are there. Now the sample space is going to be the list of all possible outcomes. So blue, brown, green, etc. A non-simple event description could be, remember, it's a description of a set of outcomes. So we could say an example could be has non-brown eyes. Okay, so just again, remember, in this one, a simple event would be the actual color observed as the outcome. The sample space would be all of the possible colors. And a non-simple event, this is just an example, it is a description of a set of outcomes. So has non-brown eyes is an example there. So let's look at some probability notation. So you're going to just add this to all the other notation we've been working with this semester so far. P means probability. So P of something means the probability of something. Capital letters are often used as a shorthand for events. For example, let A mean a person has hazel eyes, then P of A could mean the probability that a person has hazel eyes. We can also use words or other shorthands for events, and you can see some examples here. When we're looking at a range of numbers for probabilities, the possible values are going to be between 0 and 1. So for any event A, the probability of that event should be between 0 and 1 inclusive, meaning 0 would be completely impossible and 1 is certain to happen. We call probabilities that are greater than 0.5 likely and probabilities that are less than 0.5 unlikely. If you see one that is 0.5 exactly or even chance, that's a 50-50% chance. There are different types of probabilities, and we're going to start by looking at relative frequency. One of the most common ways we determine probabilities is by looking at things that have happened in the past. The probability of dying in a plane crash are 1 in 1 million. The probability of being struck by lightning in the U.S. over the course of 1 year is 1 in 700,000. An adult in the U.S. has a 50% chance of being impacted by the Equifax data breach. So these statements are based on observed events. So if you're going to try to find a relative frequency, you will say the probability of the event equals the number of times that that event has occurred divided by the number of times the procedure was repeated. Here we're going to look at an example. A company is conducting an online survey of randomly selected individuals to determine if traffic congestion is a problem in their community. So far, 320 people have responded to the survey. What is the probability that the next person that responds to the survey says that traffic congestion is a serious problem in their community? So we're saying we're finding the probability of a serious problem. So we're going to say how many say there is a serious problem. So you're going to look at the data given to you, and we have 123 out of how many total, and that's your 320. And if you put this into Excel and get a decimal answer, you'll have 0.384. Now, if you were to put this as a percent, it would be 38.4. 4%. Okay. You do not have to make that change each time. I am okay with you stopping at the decimal answer. As you're working in any homework, quizzes, tests, just be careful as to how it asks you to enter the answer. Here we have another one. We have the classical approach. Another way to determine probability is to assume all events in a sample space are equally likely. The probability of rolling an even die is 0.50. The probability of winning the raffle is 1 in 2,000. The probability of drawing an ace or a king is 8/52. These statements assume that all of the outcomes are equally likely. So if you're going to find the probability using the classical approach, you're going to say the probability of an event equals the number of ways that it can occur over the number of different simple events in the sample space. So let's take a look at an example using a die. So we have a 6-sided die. You can see a picture down in the right-hand corner. You roll a 6-sided die. You're going to find the probability of each event. So first, what is our sample space? Okay, so that means what is every event that I could get? I could get a 1, a 2, a 3, 4, 5, or 6. Okay, now let's look at if I want to roll a 3. What is the probability of rolling a 3? So the probability of rolling a 3 equals, well, how many times can I get a 3 out of my sample space? I can only get it once. And how many total pieces are in my sample space? We have 6. So 1 out of 6, which is approximately 0.167. Let's look at event B, rolling a 7. So the probability of rolling a 7. Can you get a 7 in this sample space? No, we cannot. So we're going to say 0/6 equals 0. Again, 7 is not in the sample space, so we should definitely not be able to get a 7. Now we have rolling a number less than 5. So if I'm rolling a number less than 5, that's going to be 1, 2, 3, or 4. Okay, so again, probability of rolling a number less than 5. So we're going to have 4/6, or approximately 0.667. So the fundamental counting principle is, suppose you do 2 procedures in sequence. The first procedure has m equally likely outcomes. The second procedure has n equally likely outcomes. Then the number of different ways that these procedures can be done in this order would be m times n. This principle can be extended for any number of procedures in order. So this, again, looking at that counting principle, we have roll a die and then toss a coin. How many different outcomes are there? Okay, well, I'm going to break this down so you can see why we can use that answer. If you were to actually look at every different outcome, okay, we could say rolling a die and then tossing a coin. So you could roll a 1 and get a heads. Roll a 2, get a heads. Roll a 3, heads. 4, heads. 5, heads. 6 heads. And then you got to go back and go, well, I could get 1 tails, 2 tails, 3 tails, 4 tails, 5 tails, or 6 tails. And then you could count all of those pieces. But the fundamental counting principle says that I can determine how many pieces how many numbers are in my sample space without having to write those all out. So rolling a die, you have 6 possible outcomes. Tossing a coin, you have 2 possible outcomes. So 6 times 2 gives me 12. So you should have 12 outcomes. Let's look at a combination lock that has 4 digits. So how many different lock combinations are there? Okay, you have to remember, for a lock combination, your numbers are going to be 0 to 9 on each digit. Well, if you count 0 to 9, that's 10 numbers. Okay? We have a lock with 4 digits. So I'm going to do 10 times 10 times 10 times 10, or 10 to the 4th. And that's going to give you 10,000 outcomes. You would not want to try to come up with all of those outcomes. So this shortcut gives you the knowledge of how many outcomes could be in that set. Now let's look at computer passwords. A password must have 6 letters. Could be either case, so upper or lower, doesn't matter. And then 1 number. How many passwords are possible? Okay, so if you, again, this doesn't matter if it's a case. What we're worried about is the number of letters. Now, thinking back to that example we just did, we had 4 digits, and each of them was 10, and so I ended up writing it 10 to the 4th. So if I have 6 letters, then you can say the number of letters in the alphabet, so 26 to the 6th times, and then it says, and 1 number. So that's 0 to 9, so 10. And then that will give you your number of passwords possible. So okay. Ordering a 1-topping pizza. In your order, you can select a size, so small, medium, large, a crust, crispy or hand tossed, and a topping, and there are 15 toppings. How many different pizzas can you order? Okay, so the number of outcomes for size is 3, small, medium, or large, times a crust. They have crispy or hand tossed, so that's 2, and they have 15 toppings. So 3 times 2 times 15 gives me 90 possible different pizzas that could be ordered. Looking at subjective probability is when someone determines likelihood based on intuition, personal experience, or an estimate based on knowledge of the circumstances. For example, a doctor could say to his patients, I think there's a 90% chance you will make a full recovery. This is the doctor's personal opinion based on things that he knows about the circumstance. So subjective probabilities aren't generally useful for research. Looking at simulations, sometimes it is very difficult or impossible to find the probability of an event. So we can use computer software to simulate processes and estimate the probability of an event. For example, you can actually use an Excel formula. Here you can see rand equals rand between 1 to 6, and this would simulate rolling a 6-sided die. And then we can repeat this simple simulation millions of times to estimate more complex probabilities, because we would not want to roll millions of dice. The law of large numbers. As a procedure is repeated over and over, the relative frequency of an event approaches the actual probability of the event. There is a caution here. The law of large numbers only applies to the behavior of events over a very large number of trials and does not apply to a single trial. Here you can see a statement, I've lost at this slot machine for 6 hours, so I must be close to it, so it must be close to paying out. Okay, this is one single trial of a single person playing, so this was not true in this case. If we do not know anything about the likelihood of possible outcomes, we may not be able to assume that they are equally likely. There's no point in studying for my test. I'm either going to pass or fail, so it's 50% either way. Again, this statement is not true because it's not just 50-50. Remember, there's a huge different range of grades that can be in there. Let's look at an example of texting and driving. In a study of U.S. high school drivers, it was found that 3,785 texts while driving during the previous 30 days, and 4,720 did not text while driving during that same time period. And this is from an actual study, and you can see that there. Based on these results, if a high school driver is randomly selected, find the probability that he or she texted while driving during the previous 30 days. So here you can actually see that summarization of information. We have 3,785 that text while driving, 4,720 that did not text while driving, and then we have our sum here already given to us. Whoops, hang on a second. Picked that wrong one. There you go. 8,505 total number of drivers in this sample. So your solution, remember, we're looking at what is the probability of that they were texting while driving. So we're going to take the number of students that said they text while driving, 3,785, and put it over the total number, 8,505. And then I'm going to go ahead and put that in a decimal. So I've got 0.445. So our interpretation here, and you will be doing these interpretations. So I'm going to say there is a 0.445 probability that if a high school driver is randomly selected, he or she texts while driving the previous 30 days. Okay, so again, you're stating this as an interpretation. You could have also stated there is a 44.5% chance that if a high school driver is randomly selected, he or she texts while driving the previous 30 days. So complementary events. Complement of event A. The set of all outcomes in a sample space that are not included in event A is called the complement of A. Your notation is going to be A with a bar over it. So mathematically, the following are true. The probability of A plus the probability of the complement of A equals 1. And then you should be able to find those pieces by subtracting from 1. So if you want the probability of A, you could say the 1 minus the probability of the complement of A. Or if you need the probability of the complement of A, you could say 1 minus the probability of A. And the picture here gives a good representation of what you're looking at. So the whole rectangle there would be everything inside of it would be equal to 1. And to find those pieces, you should be able to say 1 minus whatever piece you're looking for. Here we're going to look at an example of complement. So in a recent year, there were 3 million skydiving jumps and 21 of them resulted in death. Find the probability of not dying when making a skydiving jump. So since we're looking at the complement and we know how many resulted in death, then we could say the probability dying is 21 over the 3 million. If you put that into Excel, you're going to get 0.000007. And then since we're actually looking for the probability of not dying when skydiving, we can do 1 minus the probability of the dying, and that should be 1 minus 0.000007, and you should get 0.999993. So if I'm going to interpret this, I'm going to say the probability of not dying when making a skydive jump is 0.999993. Or the probability of not dying when making a skydive jump is 99.99993%. We may have to identify significant results when we're looking at probabilities. So here we have the rare event rule for inferential statistics. If under a given assumption the probability of a particular observed event is very small and the observed event occurs significantly less than or significantly greater than what we typically expect with that assumption, then we can conclude that the assumption is probably not correct. So in other words, what we're saying here is if we assume something is unlikely, but we see it happen more often than we thought it would, then we will reject our original assumption. Using probability to determine when results are significantly high or significantly low, if you have a significantly high number of successes, so this means that X successes among N trials is significantly high number of successes, if that probability of that value or more is less than or equal to 0.05. For significantly low number of successes, then you are going to be seeing that probability of that value or fewer, okay, because we're talking about a low number of successes, is less than or equal to 0.05. Now that value of 0.05 is not absolutely rigid, but that is kind of like an area that we would be looking at. Let's look back at that first example where boys and girls. So this is the one about the company that created a sex selection process that greatly increases the chances that a baby will be born a girl. So looking back at that first one, we suppose that we observed 55 girls and 45 boys, and we said that probability was about 18.4% to see this result by chance. So this study would not strongly support the company's claim. So that means that 55 is not significantly high number of girls for the 100 births. But now if you looked at the 75, where that probability was 0.000003%, we would say 75 is significantly high number of girls for 100 births. Again, we're comparing these two values to that 0.05%. 18.4 is greater than that, so because it's not less than 0.05, it's not significant, but because 0.000003% is less than 0.05, then it is significant. To practice this, you may want to look at your lab manual, pages 32 and 33. And of course, your MyStatLab homework for section 4.1. Any questions that you may have, you can put in the Microsoft Teams channel of Unit 2.